Welcome to Sanjana's Constructive Calculus with Geometrifying Trigonometry. Today we will discuss about the polyline length finding and polyline representation through geometrization of trigonometry or geometrifying trigonometry. Suppose you have seen this kind of expression where it starts with some constant value L or any number plus that L into sine of angle 1 into cosec of angle 2 plus L into sine into angle 1 into cosec of angle 2 into sine of angle 3 or cosec into cosec of angle 4 plus L sine of angle 1 cosec of angle 2 sine of angle 3 cosec of angle 4 sine of angle 5 cosec of angle 6, and in this way it continues. At every term two new trigonometry ratios are multiplied. Sometimes these angles, angle 1, angle 2, angle 3 are all same, and sometimes these angle 1, angle 2, angle 3, angle 4, angle 5, angle 6 are all different, or sometimes these angles can have a expression which are having some patterns with changing patterns, and sometimes these angles are very small. In that way, this every part of these expressions are representing some line segment. In geometrifying trigonometry, we deal with line segments, and suppose this is a polyline. The people from AutoCAD backgrounds understand that these polylines are like these. Sometimes the splines are also segregated discretely like polylines, and polylines are very important subjects, and polylines are closed or open. These are open polylines, and sometimes these polylines can close and then it is a polygon, closed polygons, and sometimes those are regular polygons, and like this. Suppose we have taken any arbitrary kind of polyline, and it can become a curve if all these polylines are, all these line segments are very small. Then it will take the behavior of a calculus, and where ds1, ds2, ds3, all these things are the small distances. We know that in calculus we take it in infinitesimal analysis, but here we are taking as the things as the discrete line segment objects are forming a polyline. Multiple line segments are forming a polyline. The initial line segment is always taken as L, that is the line 0. In geometrifying trigonometry convention, the initial line segments are always taken as the line L, capital L, that is the convention in geometrifying trigonometry. Suppose this is a polyline and every points are like this: P1, point 1, point 2, point 3, these are the nodes, the P1, P2, P3, P4, P5, P6, and in this way it is growing. First line segment is L, so in the term it is L. Second line segment has a expression which is like this, shown here in this trigonometry expression, as I have told in the starting of this video. For similar way, for line 3, line 4, line 5, line 6 are representable like these kind of trigonometry expressions, and these are summed together to find the total length of this total polyline. Let's see how can we derive this kind of things, and not only the derivation, we will construct the trigonometry expression like this trigonometry sequence like thing from the polyline. First of all, we will take the artificial construction from P1 to P3. We will construct a line segment like this, and then we will take the perpendicular from P2 on this constructed line segment, and then two angles are formed like angle 1 and angle 2. If this is taken, then this line segment, given line segment, becomes the hypotenuse of this small triangle, and this green line segment becomes the perpendicular because angle 1 is here. And sometimes if we take the mirror of this whole arrangement about this P1 and P3, then you can see that we can take the polyline in this way also. Still the length will remain same. So both of these symmetry are going to give us the same length, and if we take the other symmetries, then we can get the same length, but the geometric construction will have the different trigonometry expressions as per geometrifying trigonometry. For that reason, every symmetry of cos, sine, tan has different unique nomenclature as per the construction in geometrifying trigonometry. In our classical trigonometry, it is very ambiguous, because here we have shown that two different symmetries, the mirror image of these two line segments, were giving us the same trigonometry expression, but in actual engineering sense, these two things are different polylines. Suppose we are making a road like this, and if we are making the road like that mirror image as we have shown earlier right now, then both roads are not same. So to construct the non-ambiguous construction, then every of these cos theta, sine theta, cosec theta, tan theta, everything should have a different name for different construction protocols, for different symmetries. For that reason, geometrifying trigonometry is non-commutative but associative, and for every cos, sine, tan, sec, cosec, cot, for everything there are 4 symmetries, and every symmetry has different names, unique names, such that we can't get any ambiguous result out of that. Now from here we have seen that from angle 1 and angle 2, we can see that this green line segment constructed is L into sine of angle 1, and similarly if we forget these two things, then we will see that the new triangle so formed will have the angle 3 here, which has this one is the perpendicular already constructed. Now this line segment is known, whose length is L sine angle 1, and this line segment was not known. This line segment's length was not known, which is constructed from the trigonometry height and distance calculations, and it is now L into sine angle 1 given into cosec angle 2. So this red line segment is formed. In the same way, if we proceed here, now this line segment is found in this previous step, L sine angle 1 cosec angle 2. Now if we take it the L sine angle 1 cosec angle 2, and if we forget the previous things, and now if we construct the P2 to P4, if we construct another line segment here, and then if we construct a perpendicular from P3 on this constructed line segment, then here we will see another angle 3 will form and angle 4 will form. In the similar way, we can see that we can take the symmetry here also, and if we don't take the symmetry, then let it remain like this. And in that case also, this green line segment will have the length L sine angle 1 cosec angle 2 into sine angle 3. And when this is there, and if we take this part only from this triangle, we can find this line segment's length, the red line segment's length, as if this one is given and angle 4 is given. Now L sine angle 1 into cosec angle 2 into sine angle 3 into cosec angle 4. In this way, this additional line segment is also found. And if we continue in the same way, if we construct the line segment from P3 to P5, then we again the perpendicular here, then we can proceed to the next line segment. In this way, we can proceed one shifted line segments in this way, and then at last and to this way, we will construct another line segment, and then we will get the line segment length, total length of this whole thing. And ultimately, the whole polyline will become red when we will get the length of all the polyline. Then we will get this kind of expression. The more longer this kind of expression is, the more longer the polyline is, because the more number of line segments are involved in that case, which means more number of line segments in the polyline automatically gives us the information that the number of terms, every term is representing one edge of the whole polyline. That is, if we have a closed polygon also, then we can have this kind of long expression. And ultimately, if we see that any polygon is converging to a point, then this sequence will also converge to a single point in the 2D space. So we can do the 2D space analysis with the polygon filling curves, or while we will construct the geometry of the polylines, or if we want to do constructions of curves, then for any kind of curve where all these line segments are piecewise small line segments, ds1 ds2 are the limiting tends to 0, that is the length are limiting tends to 0. In those cases we can see that each term will represent the length of some line segments, and which are all the edges of any polyline. So any curve we can think any curve as discrete small lines are arranged to form it as the whole polyline. So any continuous curve is considered as a almost closed, almost smooth polyline, where every edge are of very small length, and all these terms in the trigonometry expression like these are actually the length of some line segments, and they have the angles hidden there. In this way, if we take any power series, if we consider any power series, or if we take any binomial theorem, any power series or any binomial theorem, any power series or any binomial theorem like objects when expanded, then some part of each term represents the angle or tangent of angle, and other multiplied part as the length of the tangent vector. So ultimately any polyline drawn in this way, any polyline or any small line segments drawn like these, small line segments are forming like this, which looks like the discontinuity. But if we draw these kind of things, then we can consider it as a curve, and all of these line segments are the terms of a infinite series, or every of these are the terms of any polyline. And it can happen that any such shapes will ultimately converging to any point or not converging to any point, and sometimes there are the odd behaviors of singularities, and sometimes it can have a chaotic like of situations, sometimes there are the self cuts. And we can explain any kind of curves through exact series of trigonometry functions as we have shown here. This is the beauty of geometrifying trigonometry, because we can handle many situations of calculus with geometrifying trigonometry, because geometrifying trigonometry handles these kind of expressions as we have shown here as the terms, which all of these terms are represented as a line segment, which are the edges of any polyline, and it can become a closed polyline or it can become a open polyline, whatever it is. But all of the kind of polylines are easily representable without ambiguity with these kind of formulations, where cos has 4 varieties A, B, C, D. In our previous videos we have already shown, and sine has the 4 varieties E, F, G, H. These varieties are of the symmetric constructions, as I have already shown you the mirror image in the starting of this video. In this way we can do calculus with geometrifying trigonometry, and every term here represents two things, a direction and also the length. Every term automatically hides the direction and the length of the tangent vector at any point of the curve. This is the beauty of geometrifying trigonometry, because with this we can handle discontinuous curves also. With this we can handle the non-smooth curves also, and for that reason geometrifying trigonometry can give us more power with the 4 symmetric cases, and which is more powerful than complex number analysis, because complex number don't take care for 4 symmetries at a time, it considers about the 2 symmetries at a time. And in geometrifying trigonometry everything is real, there is no complex term, and all the 4 symmetries of constructions are taken care at every stage of the construction. That is the beauty of geometrifying trigonometry, and with that we can handle discontinuous curves, and also discrete polylines while expressing the exact geometry non-ambiguously. And we have shown that our construction system is non-ambiguous because every four symmetries are taken care, and if the mirror image is taken, then the equation changes, because in that case we will not take the same type of sine or same type of cos, because sine is also EFGH and cosec is also taken as the RSTU, cot is taken as the VWXY, tan is taken as the IJKM. In that way, four different symmetries are taken at every stages. So we can generate the non-ambiguous constructions, and from the geometrifying trigonometry expressions we will always get a non-ambiguous unique curve, which we cannot represent with the simple kind of trigonometry expressions. Here geometrifying trigonometry is far ahead than classical trigonometry, and in that way we can handle calculus more precisely than our ordinary classical trigonometry. Thank you.